In the previous video, we talked about how you can look at the equation given to you and analyze whether or not the units in that equation make sense. Do the units of each term match each other term? So we can also go in the opposite direction. And if given a set of variables with a set of units, you should actually be able to guess what the equation is. This can be useful if you're given a problem, you're not sure how to approach it, what work to do, what to add together. You can usually get within a dimensionless factor of the correct answer just by using dimensional analysis and putting units together. So let's look at how that's done. Suppose we have a mass, which has units, of course, of kilograms, also known as, mass. And suppose we have the speed of light, which has units of meters per second, or length over time. And I want to relate these two, and from it, I want to somehow obtain an energy. And energy has units of joules, which can be broken down into kilograms times meters squared divided by seconds squared, or mass times length squared divided by time squared. So I need to use these two to get to this one. And the operations that I can use are multiplication. I can multiply these two together. I can divide these two things. I can square either one of them, or I can take the square root of either one of them. You can do other things too. You can really raise it to any power you want. But for our purposes, that will suffice. You're never going to do anything to this term. All this term serves for is to look and see if it matches what you have. So the general approach that I like to take is the first step is look here and see, well, let's not do that. Let's say the first step is to look at these two variables and see which one is more complicated. Here, this is more complicated than this. This is a quotient, this is just mass. So I'd like to start by writing down this, length divided by time, or meters over seconds. And then the second step is we're going to compare it. We're going to compare it to what we have down here. So down here, we have length over time, we have meters per second, but in this case, it's squared. So what we're going to do is we're going to say, okay, I must have to square this. After that, we look at what we need. So now we have meters squared over seconds squared, length squared over time squared, and this is perfect. Except we need mass. So we've used this variable already, so we can basically ignore it now. We haven't used this one, so we have to use this to somehow get a mass in here. It's pretty easy to do since this is a mass. So if you want to put a mass into the numerator, you're going to multiply it. So we're going to multiply this by kilograms, multiply this by mass. This gives us kilograms meters squared over seconds squared, and this gives us mass times length squared over time squared. These match these, which means we are good. So from here, we have to then get an equation. So our equation is always going to read this, E, is equal to some combination of m and c. So what did we do? Well, we took m over s, meters per second, and those were the units for c, the speed of light. We squared it. So let's substitute that back in with the speed of light. So we took c, and we squared it, and we multiplied it by m, by mass. So E equals c squared m. More commonly, you've probably heard of it as mc squared. E equals mc squared. That's all there is to it. You're done when you get there. Let's do a few more examples, though, to make sure that this is clear. Suppose I give you a velocity which has units of meters per second, or length over time, and I give you a radius, which has units of meters, more generally length. And from that, I want you to obtain an acceleration. So, the acceleration will have units of meters per second squared, or length over time squared. So, again, the first step is to look at which of these is more complicated. Velocity has more complicated units. So let's start just by writing down L over T, or meters per second. And then we have to compare it to what we want. We want length over time squared, we want meters over second squared. We want acceleration. So how can we get this closer to this? Well, this has a time squared, a second squared, so let's square it. When we square them, we now have meters squared over second squared and length squared over time squared. And we've used velocity, we're done with velocity. So now we need to cut one of the length units. We only want a meter and a length. We don't want a meter squared and a length squared. So how can we get that gone? Well, let's look at the other unit we have left. We have a radius left, which has units of mass and length. One of the legal operations is division. So let's divide by meters, divide by length, and then that squared cancels that squared cancels that. You're left with meters over second squared, length over time squared, which matches what we wanted. So now we have to back substitute in the actual properties. So, again, let's look at what we did. We took velocity, that was more complicated, and we squared it. So we'll have A is equal to, that's always going to be the first thing, A equals, we squared velocity, so V squared. Then what did we do? We multiplied by the radius, by R. So you have V squared, we divided. We divided by R. We divided by the unit of length, and that got rid of the square for us. So you divide by R. And this is your answer. So again, you just look at which is more complicated, write it down, see if you can manipulate it to get closer to this, then look at the other variables you're given, and try to put them in such a way as you get closer to the units again. And then you've got to back substitute in the actual properties. Let's do another one. Suppose I give you a mass, I give you the acceleration due to gravity, and I give you a height. This has units of kilograms, or mass. This has units of meters per second squared, or length divided by time squared. And this has units of meters, or length. And I want you to use that to find, an energy, which I'm going to write as U. We'll learn why later on in the course. So this energy has units of joules, which can actually be broken down to kilograms times meters squared over seconds squared, which is equal to mass times length squared divided by time squared. Just depending on what unit system you prefer. So from here, we're going to start again. Which of these is the most complicated? L over T squared is the most complicated. So we're going to write L over T squared down. M meters over second squared, write it down. So, compare it to this. Can we manipulate it to get it closer to this? Well, if we square this to try to make the length and meters match here, then this is going to become to the fourth power. And we don't have any other times such that we can cancel that out. So I'm just going to leave it alone. I'm not going to do anything to it. So now we've used our acceleration due to gravity. And now we're looking at the other two. So let's look at the first one. Let's look at mass. These are both relatively the same complexity because they're just one unit. So mass, we see a mass up here on top. So let's just multiply by mass to get a mass on top. So I'll multiply by kilograms, multiply by mass. We get kilograms times meters per second squared, and we get length times mass divided by time squared. So now we've used mass, which leaves us only with h, height. So height, let's look at what we have. So we need a meter squared still. We need an L squared. We only have 1. Luckily, height provides us with 1 meter, 1 length. So if we want to square these, we can just multiply by meters, multiply by length, and then you end up with kilograms times meters squared divided by seconds squared, and mass times length squared divided by time squared, and those units match these. Which means we're set, except we still need to come up with an equation. So again, you're always going to start with u is equal to, and then you're going to retrace your steps. We started with g, we didn't do anything to it, so we'll write down g. Then we multiplied by mass, so let's multiply by mass. Finally, we multiplied by h in order to get the L squared, so now we multiply by h. So now you have a relation that energy is equal to gmh. More commonly, you'll see it as mgh, but multiplication can be interchanged, so it's fine. So that answer is your final answer, and you are set. So that's all for that. Let's do yet another example. Examples are good and will help you understand what's going on. So, suppose, in this example, I give you an area, use the same color, I give you an area which has units of meters squared or length squared. I give you a force which has units of newtons, but you break that down, and it has units of kilograms times kilograms times meters divided by seconds squared. And this would be mass times length divided by time squared. And from that, I want you to come up with an equation for pressure, where pressure has units of kilograms divided by meters times seconds squared. So again, we're going to start off by picking the most complicated of the units that we want to manipulate to get this one. So let's look, and this is definitely more complicated than this. This is a multiplication, division, square. This is just a square. So we're going to write it down. So we have kilograms times meters over seconds squared, or mass times length divided by time squared. And compare it to what we have here. Let me write down the generalized units here. So this is mass divided by length times time squared. So we'll compare it to what we have there, and we can see that the kilograms over second squared, the meters over mass over time squared, matches. It's only the length units that are on the wrong side of the fraction. So let's keep this the same, because if we square this or square root this or anything, then it's just going to get more complicated for us. Instead, all we have to do is find a way to move this down here. So let's say we're done with the force, which leaves us to look at the area. The area has units of length squared. So let's look at this, and how can we use length squared to get a single meter on the bottom? Well, it turns out if you divide, when you divide exponents, you subtract them, right? So let's divide by a meter squared. Let's divide by length squared. And a square gets rid of that. This square makes that disappear. And you end up with kilograms divided by meters times seconds squared, and mass divided by length times time squared. So this matches what we wanted, which is great. Now we just have to go backwards. So we start with pressure is equal to, as always, and what did we do? Well, we took the force, and we didn't do anything to it. So I'm just going to write down the force. Then we took our area, meters squared, length squared, and divided it by it. So F over A. And that's the equation for pressure. So again, analyze the units, put them together. It's like a puzzle, figure it out, and then back substitute for the values that you're interested in. We'll do one final example, which is pretty straightforward, but can be a little tricky because you might not have seen this unit before. So let's say I give you a force and a charge. Charge is the new one. So force has units of, as I've said, newtons, but we'll simplify. So we get kilograms times meters per second squared, and we get, we get mass times length over time squared. Q is a charge and has units of coulombs, which is written as a C, and charge, which I think is also written as a C. So we're just going to leave those there. And what I want you to do is combine them in order to get units of the electric field strength. So this E does not equal energy. This E is for electric field strength, and it has units of kilograms times meters divided by coulombs times seconds squared. So, we'll translate this into the general units. Mass times length over charge times time squared. So we're going to start again by looking at these two and picking the more complex one. Force is more complicated units than charge, and we're going to write it down. So kilograms times meters over seconds squared, and we have mass times length over time squared. Compare it to what we have. Well, let's see. Okay, kilograms, meters over seconds squared, mass length over time squared. This matches exactly. We just need a C on the bottom. So I'm not going to touch it. I'm going to leave it alone. So we're done with force. How can we get charge in there? Well, we need a C on the bottom. We have a C. Let's just divide by C. So both sides, we're going to divide by C, and this is going to give us kilograms times meters divided by coulombs times seconds squared. We have mass times length divided by charge times time squared. The units are good. So we're going to look at our electric field, and it's going to be equal to what? We have to go back and back substitute, retrace our steps. We took a force, and we didn't do anything to it, and then to get the C on the bottom, we divided by charge. So this is your equation for electric field strength. So I just want to point out too, you don't have to do it both ways. You don't have to use both units. I've been doing it the whole time because different people prefer different ways of doing it. Both are equally valid, will get you the right answer, get you the right equation, and all is good and well. So this is how you're able to use units to guess equations. And you can use this actually to guess answers in problems. If you're given certain things and you don't know what the answer is, you don't know how to get there, you can often just combine it and guess it. The only problem with this system is you'll recall from the previous video that numbers have no units. So we cannot predict any numbers that are in these equations. These equations are only good to a dimensionless factor. What that means is this could be E equals 2F over Q, or F over Q pi. It could equal a whole bunch of things with numbers. But the key relationships, the proportions, those are the really important things anyways. And that's what we're able to get by using the units to guess the equation.